today, guys, is we're looking at logarithms. So we have looked at what a logarithm is, but we're going to look at what the graph of a logarithmic function is. So a logarithmic function is a function in the form of y equals log base a of x. And we have the logarithmic function, y equals log base a of x, is the inverse of an exponential function y equals a to the power of x. And this is because their graphs are reflections of each other in the line y equals x. So if you do extension 1 maths and you've looked at inverse functions, this is pretty much the same as that, and I'm going to teach it like that to everyone, okay? But so you'll have a little bit of an upper hand. So what we have and what we've learned is log BAP in previous lessons, and log BAP with our logarithmic function, how we use that is it undoes our exponential function. So what we're going to do is we're going to sketch the graph y equals x. I believe it's already there for you. Aren't you lucky? And y equals 2 to the power of x and y equals log base 2x on the same number plane. So we're going to need 2 different coloured pens, or I can give you a highlighter and you can do it in the same colour and go over them in a highlighter. But the first one that we're going to draw is our exponential function, and we looked at drawing exponential functions earlier in this topic at the end of last term if you're away. So y equals 2 to the power of x, it has an asymptote at y equals 0. So what that means is it's not going to go through the line y equals 0. Now, what we can do is we can just do a table of values using our calculator to find some key points. But we have that it has a y-intercept at the coordinates 0, 1. Okay, so our y-intercept's at 0, 1. We then have, when we go 2 to the power of 1, so when x equals 1, so when x equals 1, we get that y is equal to 2. When we have x equals 2, we get y equals 4. When we have x equals 3, we get y equals 8. And if we were to do 4, that would be 16, but 16 is off our graph. The other value that we're going to look at is what happens at -1. At -1, it is a half. So 2 to the power of -1 is a half. Now, we're going to draw our graph of our exponential function, making sure that we do not go below our x-axis. And it's a nice smooth curve going through our points like so. Arrows on either ends. And we are actually going to, for the purpose of this, make sure that we write our coordinates on our points. Actually, I might move my 0, 1. Okay. So that is what our exponential function is. Oh, I need to label my function y equals 2 to the power of x. Okay. Now, how we get our inverse function, or how we get what inverse function means, is when we do our inverse function, it means to swap the variables. Or swap the coordinates is probably better to write. Okay. So what that means is our x coordinate is going to become our y coordinate, and our y coordinate is going to become our x coordinate. Okay. So here we had that these were our x, or I will do it in pink underneath. These were our x, y. Okay. And what we're going to do is we have our function of y equals log base 2 of x. Okay. We are going to, in order to get the coordinates for y equals log base 2 of x, what we have to do is we have to swap the x and y values so that they're now in the form yx, technically. So what that means is our 0.01 is going to become 10, our 0.12 is going to become 21, our 24 is going to become 42, 38 becomes 83, and minus 1/2 becomes 1/2 minus 1. These are the coordinates of our log function, and our y equals log base 2 has an asymptote at, instead of, our exponential had an asymptote at y equals 0, so our log function has an asymptote at x equals 0. Does that make sense? Okay, so if we were to then plot those coordinates, so 1/2, -1, we have 1, 0, we have 2, 1, we have 3, we have 2, hang on, we have, we don't have a 3 there, that's okay. We have 4, 2. We don't really need the 3, we have the general shape. So then what we have is our logarithmic function is just in that side of our y equals x line, and we have our coordinates that we need to plot on as well. Okay, and this is our y equals log base 2 of x. So the whole purpose of this little exercise or this little example is for you to see the relationship between an exponential function and a logarithmic function and how they're the inverse of each other, just like how multiplication and division are the inverse of each other. Okay, so they're opposite the line y equals x. Now, to be completely honest, when we sketch exponential or logarithmic functions, we just use a table of value using our calculator to sketch it, like what we just did there. So we don't always have to do the exponential to get the logarithmic function. Does that make sense? So in a moment when you have a go at sketching independently, we're just going to use a table of value to plot some points, draw a nice smooth curve. Now, unless our function gets shifted horizontally, our asymptote for a log function is always going to be at x equals 0. Now, they were logs with base 2. What we're going to do in our next example is we're going to look at our y equals log base e of x, where we have our base e and it's our natural logarithm, and we write that as y equals ln x instead. Okay. What we have is we are going to sketch our graph of y equals x. It's already there for us. Our y equals e to the power of x minus 1, and our y equals log base e of x minus 1. Now, our y equals e to the x minus 1 is the graph. It has a parent graph of y equals e to the x, but it has been vertically translated. So translated is a fancy word for shifted, moved, 1 unit down. Okay, so that's what that minus 1 does, is it picks up our graph and it shifts it 1 unit down. So normally with an exponential, the normal asymptote is normally at y equals 0, but because we have shifted it down, our asymptote is at y equals -1 instead. So at -1, which is here on our graph, we are going to draw a dotted line because that's where our asymptote is going to be. just so that we can clearly see it. Now, how do we sketch an exponential function? What do we do to sketch an exponential function? If I wasn't standing up here in front of you to sketch an exponential function, what would you do? A table of values, all right? You're just going to, in your calculator, so we're not going to do all those swapping, the variables. In our calculators, what we're going to do is we're going to get our point minus 1. So we're going to get E. So we press Shift 8 on our calculator to the power of -1 to start off with, and then minus 1. And we get, at -1, it's like negative 0.6-ish. Okay? Then we're going to substitute in x equals 0. It's at 0. Then we're going to substitute in x equals 1. So e to the power of 1 minus 1, it's at 1.7. E to the power of 2 is at 6.4. This is me rounding to 1 decimal place 2, by the way. And we have e to the power of 3 is 19. Okay, so it's going to be off the graph. So from there, we can then sketch our exponential function. Okay, making it go nice and steep. That little bit's a bit dodge. I'll just do that again. One, it's at 1.7. 2, it's at 6.4. Nice, smooth curve. Believe it or not, it's easier to draw this on paper than it is on the iPad. I just get to erase it easier. All right, we're going to just put at least 1 point on. We're going to make sure that we have our intercept at 0, 0 listed. And then I'm just going to do 2 and 6.4 as my other point. Okay. Now, what we want to do for our other function, our y equals log base e of x minus 1. So y equals log base e of x minus 1 is also written as y equals ln x minus 1. And so what that is we have our parent graph. So this is like a child, I suppose, when we think about like parents and children. So our parent graph of y equals ln x is vertically translated 1 unit down. Okay, so what that means is we're just going to put it into a table of values. So we're going to get ln up on our calculator. We're going to substitute in, if we substitute in ln negative 1 of minus 1, you're going to get a math error, okay? The reason why every log function has an asymptote at x equals 0. Oh, hang on, is this one? Yes. Okay, so x equals 0 is our asymptote. Okay, so we're going to start off by substituting in 1. When we substitute in 1, we get negative 1. When we substitute in 2, we get negative 0.3. When we substitute in 3, we get 0.09. When we substitute in 4, we get 0.38. Okay, and then we can draw the general shape of our logarithmic function. So sort of looking like when we were drawing our hyperbolas. Putting on a point. Okay. Now, what you'll notice with these two, these ones aren't complete inverses of each other, okay, because they have been altered, because they have been translated differently. So they're not always going to be the inverse of each other. We also don't need to worry about our x-intercept with this one. Okay, turn to the next page when you're ready. Thank you. Yeah, it is very cold. All right, does anyone still need that? So what we're going to do now is we're going to sketch we're not going to. You're going to have a go of using your calculator to sketch the graph of y equals 3 log base 10 of x plus 4. Now, if we have log base 10, what button are we pressing on our calculator? Log, right? So in your calculator, you're going to go 3 log a value plus 4. Where do you think our asymptote is going to be for our function? Our asymptote is at x equals 0. Okay, and what you will notice is it's only ever so slightly going up. Okay, you need to make sure you label a key point. I do not care for log functions. Don't worry about your x-intercept. Okay, what do we think the domain is? So our asymptote to infinity, where's our asymptote at? 0, so it's going to be domain is 0 to infinity. What's our range? What y values can the function be? All of them, right? So if it's all of them, it's going to be negative infinity to infinity. And that generally is the domain and range for any log function.